Introduction: the cosmic coincidence we exist. That might seem like the most obvious statement possible, but it's actually one of the most profound mysteries in all of science. The universe we inhabit is governed by fundamental constants numbers that determine the strength of forces, the masses of particles, the rate of cosmic expansion. Change any of these numbers even slightly, and the universe would be drastically different. Stars wouldn't form, chemistry wouldn't work, life as we know it would be impossible. Yet here we are. The constants have exactly the values needed for complexity, structure, and ultimately consciousness to emerge. The universe appears fine-tuned for life with extraordinary precision. That seems to require explanation. This is the fine-tuning problem, and it's one of the deepest puzzles in modern physics. The Anthropic principle offers an approach to understanding it, but the implications are controversial, touching on physics, philosophy, and even theology. By the end of this exploration, you'll understand the evidence for fine-tuning, the various explanations proposed, and why this question connects to the multiverse, the nature of scientific explanation, and our place in the cosmos. The fundamental constants. Let's start with the basics. Physics is built on fundamental constants, numbers that appear in the laws of nature and determine how the universe behaves. The speed of light in vacuum is one such constant, approximately 299,792 kilometers per second. This isn't arbitrary. It's woven into the structure of spacetime itself, appearing in Einstein's equations relating space and time, energy and mass. The gravitational constant determines gravity's strength. It tells you how much force exists between two masses separated by a given distance. Change this number, and planets would orbit differently, stars would burn at different rates. The entire cosmic architecture would shift. Planck's constant sets the scale for quantum mechanics. It determines how the quantum world is how significant quantum effects are compared to classical behavior. The fine structure constant describes the electromagnetic force's strength. It appears in calculations of atomic structure, chemical bonding, how light interacts with matter. The masses of fundamental particles, electrons, quarks, neutrinos are constants. The electron mass determines atomic sizes, chemical reaction rates, the properties of all matter. There are roughly 20 to 30 such fundamental constants, depending on how you count. Some might be related, reducing the number of truly independent constants, but we don't know for sure. What we do know is that these numbers determine everything about how the universe works. And here's the strange part. Many of these constants appear fine-tuned. They have values that seem improbably well-suited for the existence of complex structures, chemistry, and life. The carbon resonance, Hall's prediction, one of the most famous examples of apparent fine-tuning, involves carbon, the element essential for all known life. Carbon is synthesized inside stars through a process called stellar nucleosynthesis. Stars are nuclear furnaces, fusing lighter elements into heavier ones. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into oxygen, and so on up the periodic table. But there's a problem. The straightforward fusion of 3 helium nuclide into carbon shouldn't work. The reaction requires 3 helium nuclide to come together simultaneously, which is extraordinarily unlikely to produce the carbon we observe throughout the universe. In the 1950s, astrophysicist Fred Hoyle realized that for carbon to be abundant, there must be a resonance and excited energy state of the carbon nucleus that exactly matches the combined energy of 3 helium nuclei. This resonance would dramatically increase the reaction rate, making carbon production feasible. Hoyle predicted this resonance must exist at a very specific energy level, around 7.65 million electron volts above carbon's ground state. At the time, no such resonance had been observed, but Hoyle was so convinced because we exist, and we're made of carbon, so carbon must be producible in stars that he insisted experimenters look for it. They found it. The resonance exists at 7.656 million electron volts, almost exactly where Hoyle predicted. This is remarkable. The energy level of this resonance depends on the strong nuclear force's strength and other fundamental constants. If these constants were slightly different even by a few percent, the resonance would be at the wrong energy. Carbon production would be suppressed. The universe would be carbon poor. Without abundant carbon, chemistry as we know it wouldn't exist. Carbon's unique bonding properties, its ability to form long chains, complex molecules, the entire foundation of organic chemistry depend on its nuclear and electronic structure. Hoyle's prediction is often cited as an early example of anthropic reasoning. He essentially argued, we exist, we're made of carbon, therefore stars must produce carbon efficiently. Therefore, its resonance must exist. And it does. But it raises a disturbing question. Why does the resonance have exactly the right energy? Is it coincidence, design, or something else? The deuterium bottleneck. Another example involves deuterium, an isotope of hydrogen with 1 proton and 1 neutron. In the Big Bang, the universe began hot and dense. As it cooled, nuclear reactions occur, synthesizing the first atomic nuclei, mostly hydrogen, some helium, tiny amounts of lithium, and other light elements. This is Big Bang nucleosynthesis. Deuterium is a crucial intermediate step. To make helium, you first need to make deuterium. A proton and neutron must bind together. Then deuterium nuclei fuse with protons or other deuterium nuclei to form helium. To deuteron, the deuterium nucleus is barely bound. Its binding energy is only 2.2 million electron volts. This is small compared to other nuclei. The deuteron is fragile, easily broken apart by energetic photons. If the strong nuclear force were slightly weaker, the deuteron wouldn't bind at all. No deuterium means no helium production. In the Big Bang, stars would still make helium eventually, but the universe would start with almost pure hydrogen. More interestingly, if the strong force were slightly stronger, the deuteron would be more tightly bound. This sounds good, but it causes problems. A more tightly bound deuteron would form earlier in the Big Bang when temperatures were higher. This would lead to almost all hydrogen being converted into helium. A universe with no hydrogen, only helium, and heavier elements would be very different. Hydrogen is the simplest element, the most abundant, the fuel for the longest-lived stars. Stars made of helium burn hotter and faster, living only millions of years instead of billions. Complex chemistry requires long-lived stable environments. Moreover, water requires hydrogen. Without hydrogen, no water. No water, no life as we know it. The strong force's strength appears finely tuned to produce a universe with both hydrogen and helium in useful proportions. The cosmological constant problem, perhaps the most striking fine-tuning, involves the cosmological constant related to the energy density of empty space itself. Einstein introduced the cosmological constant in 1917 as a term in his gravitational field equations. He later called it his biggest blunder, but it turns out to be real and profoundly important. Empty space has energy. This vacuum energy, or dark energy, causes the universe's expansion to accelerate. We observe this acceleration through distant supernovae and other cosmological measurements. The cosmological constant describes vacuum energy's density. And this density is incredibly small but not zero. It's about 10 in natural units. That's a decimal point followed by 119 zeros, then a 1. This is extraordinarily tiny. But here's the problem. Quantum field theory predicts vacuum energy should be much larger. When you calculate the contribution from quantum fluctuations of all fields, you get a number around 10, not 10. That's a discrepancy of 10, followed by 240 zeros. This is the worst prediction in physics history, off by more than 100 orders of magnitude. Yet the cosmological constant must be small. If it were much larger, say 10 instead of 10, the universe would expand so rapidly that galaxies, stars, and planets couldn't form. Matter wouldn't have time to clump together before being torn apart by accelerating expansion. If the cosmological constant were negative and large in magnitude, the universe would collapse before stars could form. The observed value is just barely small enough to allow structure formation. It's as if someone carefully tuned the knob to exactly the right setting, not too large, not negative, but precisely in the narrow range permitting galaxies and life. Why? We don't know. This is the cosmological constant problem, one of theoretical physics' deepest mysteries. The Higgs field and particle masses. The Higgs field, discovered experimentally in 2012, gives particles their masses through their interactions with the field permeating all space. The Higgs field strength, its vacuum expectation value, determines the masses of quarks, electrons, and other particles. Change the Higgs field strength, and particle masses change proportionally. If the Higgs field were stronger, particles would be heavier. Heavy electrons would make atoms smaller and chemistry different. Heavy quarks would make protons and neutrons unstable or alter nuclear physics fundamentally. If the Higgs field were weaker, particles would be lighter. Light electrons would make atoms huge and weakly bound. chemical bonds would be fragile. Light quarks would make nuclei less stable. The Higgs field's actual strength appears fine-tuned to produce stable atoms, robust chemistry, and the complex structures necessary for life. Moreover, the Higgs mass itself, about 125 GeV, discovered at the Large Hadron Collider, is peculiar. Quantum corrections should make it much larger, near the Planck energy scale, where quantum gravity becomes important. That's 10 GeV, 14 orders of magnitude higher than observed. This is the hierarchy problem. Why is the Higgs mass so much lighter than quantum corrections predict? Some mechanism must cancel almost all the quantum corrections, leaving only a tiny remainder. We don't know what mechanism. This fine-tuning is technical rather than cosmic. It's about balancing quantum corrections, rather than choosing an initial value. But it's still puzzling. Some physicists propose supersymmetry, a symmetry between particles and forces that naturally cancels quantum corrections, stabilizing the Higgs mass. But experiments at the LHC haven't found supersymmetric particles, ruling out the simplest versions of the theory. The Higgs mass remains mysteriously light, seemingly fine-tuned. The flatness problem. The universe's spatial geometry is remarkably flat. Measurements of the cosmic microwave background radiation show spatial curvature is extremely close to zero. The universe is neither significantly curved like a sphere nor saddle-shaped. It's flat to within measurement precision. But this flatness is unstable in the standard Big Bang cosmology. Any small deviation from perfect flatness grows exponentially over time. If the early universe had even tiny curvature, it would quickly become dominated by that curvature, making the universe either rapidly collapse or expand so fast that structure couldn't form. For the universe to be as flat as we observe today, the early universe, say, 1 second after the Big Bang, must have been flat to incredible precision. The curvature parameter must have been equal to 1 to within 1 part in 10 or better. Why was the early universe so precisely flat? It seems like fine-tuning, setting initial conditions to extraordinary precision, for no apparent reason. Inflation theory, proposed by Alan Guth in 1980, solves this. During inflation, the universe underwent a brief period of exponentially rapid expansion. This expansion stretched space so much that any initial curvature was diluted away, leaving the observable universe flat regardless of initial conditions. But inflation itself requires fine-tuning. The inflaton field, the field driving inflation, must have particular properties. Its potential energy must have a specific shape. Why does the inflaton have those properties? We've pushed the fine-tuning problem back but not eliminated it. The strength of gravity is extraordinarily weak compared to other forces. The electromagnetic force between two protons is 10 times stronger than their gravitational attraction. You experience this daily. A small refrigerator magnet overcomes Earth's entire gravitational pull on a paperclip. The electromagnetic force in the magnet defeats the gravity of a planet with mass 610 kilograms. Why is gravity so weak? We don't know. This is the hierarchy problem. In another guise, why are the force strengths so vastly different? But gravity's weakness is essential for life. If gravity were much stronger, stars would burn hotter and faster. A star like the Sun might last only millions of years instead of billions. Insufficient time for complex life to evolve. Stronger gravity would also make planets smaller and denser. Surface gravity would be higher, potentially preventing the development of large organisms or complex structures. If gravity were much weaker, stars wouldn't ignite at all. Gravitational compression wouldn't be sufficient to achieve the temperatures needed for nuclear fusion. The universe would be cold and dark, filled with hydrogen gas that never forms stars. The gravitational constant appears fine-tuned to produce long-lived stable stars and habitable planets. The strength of nuclear forces. The strong nuclear force binds protons and neutrons into atomic nuclei. It must overcome the electromagnetic repulsion between protons. Positive charges repel, yet atomic nuclei hold together. If the strong force were slightly weaker, only hydrogen would be stable. Heavier nuclei would be unbound. The periodic table would have one entry. Chemistry would be trivial. If the strong force were slightly stronger, the diproton to protons bound together would be stable. In our universe, the diproton is unbound. The strong force isn't quite strong enough to overcome electromagnetic repulsion between two protons. You need a neutron involved to make stable nuclei. But if diprotons were stable, Big Bang nucleosynthesis would be dramatically different. Hydrogen would rapidly convert into diprotons, then into helium and heavier elements. The universe would have no hydrogen. Again, no hydrogen, no water, no long-lived stars. Life as we know it becomes impossible. The weak nuclear force is responsible for certain radioactive decays and neutrino interactions. If the weak force were significantly different, stellar nucleosynthesis would be affected. Some reactions that produce elements necessary for life might not occur. The strengths of both nuclear forces appear to fall within narrow ranges, permitting the chemistry required for life. Dimensionality of space: we live in 3 spatial dimensions. We can move forward, backward, left, right, up, down. Why 3? In 2 spatial dimensions, complex structures are difficult. You can't have complex networks, bytes, circulatory systems, neural connections without intersections. Knots can't exist in 2 dimensions. In 4 or more spatial dimensions, atoms wouldn't be stable. The mathematics of electromagnetism and gravity changes with dimensionality. In 4 spatial dimensions, planetary orbits are unstable. Atoms don't have stable energy levels the way they do in 3 dimensions. Stable atoms require 3 spatial dimensions. Stable orbits require 3 dimensions. Complex structures require 3 dimensions. There might be additional dimensions beyond the 3 we experience, curled up at tiny scales as proposed in string theory, that the 3 large spatial dimensions we observe seem necessary for complexity and life. This raises questions. Why does space have 3 large dimensions? Could it have been different? Is this fine-tuning, or is there a deeper explanation? The arrow of time has a direction. We remember the past, not the future. Eggs break but don't spontaneously reassemble. Entropy increases, disorder grows over time. This arrow of time emerges from the second law of thermodynamics. Entropy tends to increase in closed systems, but the fundamental laws of physics are time-symmetric. They work equally well forward or backward in time. The arrow of time ultimately derives from the universe's initial conditions. The Big Bang began in a low-entropy state, highly ordered, uniform, smooth. As the universe expands and evolves, entropy increases, and time's arrow emerges. But why did the universe begin in a low-entropy state? This requires fine-tuning of initial conditions. The initial state could have been high-entropy, chaotic, disordered. Instead, it was remarkably smooth and uniform. Roger Penrose calculated that the probability of the universe beginning in such a low-entropy state is around 1 in 10,123. That's incomprehensibly small a number you can't write down even using all atoms in the observable universe as digits. This seems like extraordinary fine-tuning, yet without it, there would be no thermodynamic arrow of time, no distinction between past and future, no evolution from simple to complex structures. The multiverse solution: one explanation for apparent fine-tuning is the multiverse hypothesis. If infinitely many universes exist with different constants and laws, it's unsurprising that we find ourselves in one that permits life. The Anthropic principle, in its weak form, states, we observe the universe to be compatible with our existence because we couldn't exist in a universe incompatible with life. This is tautological, but potentially explanatory. If there's only one universe, fine-tuning is mysterious. Why do the constants have life-permitting values? But if countless universes exist with different constants, some will by chance have the right values. We necessarily find ourselves in one of those rare life-permitting universes because we couldn't exist elsewhere. It's a selection effect, like asking why we live on a planet with liquid water and breathable atmosphere. Not all planets have these properties, but intelligent observers must live on planets that do. Similarly, not all universes permit life, but intelligent observers must live in universes that do. Eternal inflation: one mechanism for generating a multiverse is eternal inflation. In this scenario, inflation, the rapid expansion in the universe's early moments, doesn't end everywhere simultaneously. Some regions stop inflating and become pocket universes, like ours. Other regions continue inflating, spawning more pocket universes. This process is eternal and self-sustaining, producing infinitely many universes with potentially different properties. The constants and laws might vary between these pocket universes. In some, the cosmological constant is too large. Those universes expand so fast that structure never forms. In others, the strong force is too weak. Those universes have no atomic nuclei beyond hydrogen. Only in rare universes with the right combination of constants does complexity emerge. We inhabit one such universe because we couldn't exist in the others. String theory landscape: string theory, a candidate for a unified theory of physics, predicts an enormous landscape of possible vacuum states each corresponding to different physics. The extra dimensions required by string theory can be curled up in countless different ways. Each configuration produces a different effective physics, different particle masses, force strengths, constants. The number of possible configurations vast estimates range from 10 to 10 or more. This is the string theory landscape. If all these configurations are realized in different regions of a multiverse, then again we have a selection effect. Most universes in the landscape don't permit life. We find ourselves in one that does. Criticisms of the multiverse hypothesis is controversial. Critics argue it's not falsifiable if we can never observe other universes. How can we test the hypothesis scientifically? Moreover, if everything possible happens somewhere in an infinite multiverse, doesn't that undermine physics' predictive power? We can explain any observation by saying it happens in this universe, and other things happen in other universes. Some physicists argue the multiverse is a theory of anything that predicts nothing. Others respond that we can make statistical predictions about what typical life-permitting universes look like, and test whether our universe matches those predictions. The debate continues. The multiverse remains a live hypothesis, but not a confirmed theory. Design and intelligent design. Another explanation for fine-tuning is design. The universe was intentionally created with these specific constants to permit life. This is the oldest explanation, dating back millennia. Ancient philosophers and theologians argued the world's apparent design points to a designer. The fine-tuning of fundamental constants provides what some see as the strongest modern version of this argument. The fine-tuning is so precise, so improbable, that random chance seems inadequate, and the multiverse hypothesis, while avoiding a designer, requires positing infinitely many unobservable universes. To some, a single design universe is more parsimonious. This touches on the intelligent design movement, which argues that certain features of the universe and life are best explained by an intelligent cause. Fine-tuning of physical constants is one such feature. However, most scientists reject intelligent design as an explanation within science. The problem is that a designer doesn't make testable predictions. It doesn't tell us what constants should be or how to calculate anything. It's not falsifiable. There's no observation that could disprove it. Science requires natural explanations in terms of physical processes and laws. Invoking supernatural designers falls outside science's scope, regardless of whether such designers exist. Moreover, the design hypothesis raises new questions. Who designed the designer? Why did the designer choose these particular constants? The explanation becomes as mysterious as what it's trying to explain. That said, fine-tuning remains striking. Whether explained by multiverse, design, or something else, the precision required for life is genuine and demands acknowledgement. The weak and strong anthropic principles. The anthropic principle comes in two main versions, weak and strong. The weak anthropic principle states, we observe the universe to be compatible with our existence because we couldn't exist in a universe incompatible with conscious observers. This is tautological, but potentially explanatory when combined with the multiverse. If many universes exist with different properties, we necessarily find ourselves in one permitting life. It's a selection effect, no more mysterious than fish finding themselves in water. The strong anthropic principle states, the universe must have properties permitting life to develop at some point. This version suggests life or consciousness is somehow necessary, built into the cosmos fundamentally. The strong version is much more controversial. It implies teleology, purpose, or goal-directedness in nature. Most physicists reject this, seeing the universe as fundamentally purposeless, with life emerging accidentally where conditions permit. Some interpretations of quantum mechanics, like John Wheeler's participatory universe, suggest observers play a fundamental role in bringing reality into existence. In this view, the universe needs observers to exist, so it must have properties permitting observers to arise. This borders on metaphysics and remains highly speculative. Most physicists stick with the weak anthropic principle if they use anthropic reasoning at all. The hierarchy problem revisited. Let's return to the hierarchy problem. Why the Higgs mass is so much lighter than quantum corrections predict. Quantum field theory says virtual particles constantly pop in and out of existence. These quantum fluctuations contribute to particle masses. For the Higgs boson, contributions from all possible virtual particles should make it incredibly heavy. Near the Planck mass, where quantum gravity becomes important, that the Higgs mass is about 125 billion electron volts. The Planck mass is about 10 to the 19th billion electron volts. That's 17 orders of magnitude heavier. For the Higgs to be as light as observed, all these quantum corrections must cancel almost perfectly, leaving only a tiny remainder. The cancellation requires fine-tuning to 1 part in 10 to the 17th. This is technical fine-tuning about quantum calculations, not cosmic initial conditions. But it's equally puzzling. Supersymmetry was proposed to solve this. Supersymmetric partner particles would contribute corrections of opposite sign, automatically canceling standard particle contributions. No fine-tuning needed. But experiments haven't found supersymmetric particles. The simplest supersymmetric models are ruled out. If supersymmetry exists, it's more complex than we hoped. Alternative solutions exist. Maybe there are extra dimensions that change how quantum corrections work. Maybe the Higgs isn't fundamental, but composite, made of more basic constituents. Maybe there's new physics we haven't imagined. Or maybe it really is fine-tuned, perhaps in a multiverse of universes with different Higgs masses. We inhabit one where it's light enough for atoms to be stable and chemistry to work. The lithium problem Big Bang nucleosynthesis produced hydrogen, helium, and trace amounts of lithium in the universe's first minutes. We can calculate how much of each element should have been produced based on known physics. For hydrogen and helium, observations match predictions beautifully. But lithium is a problem. We observe only about 1/3 as much lithium-7 as predicted. Where did the rest go? This is the cosmological lithium problem, and it's been puzzling astrophysicists for decades. Several explanations have been proposed. Maybe stars destroyed lithium over billions of years. Maybe our understanding of nuclear reaction rates is slightly wrong. Maybe there's new physics affecting lithium production or destruction. None of these explanations is entirely satisfactory. The lithium problem remains unsolved. Interestingly, if the baryon-to-photon ratio, the number of protons and neutrons per photon in the early universe, were slightly different, lithium production would change dramatically. The observed ratio produces the right amount of hydrogen and helium, a too much lithium-7. Is this fine-tuning, or just an unsolved problem in our understanding of nuclear physics and stellar astrophysics? We don't know yet. Nuclear stability and the periodic table. The existence of stable atomic nuclei is itself remarkable, and depends on fine-tuning of the strong and electromagnetic forces. Protons repel each other electromagnetically like charges repel. For nuclei to be stable, the strong nuclear force must overcome this repulsion. The strong force is attractive at short ranges, pulling protons and neutrons together. But the balance is delicate. If the strong force were slightly weaker, only hydrogen would be stable. Two protons couldn't bind together even with neutrons helping. No periodic table beyond hydrogen. If the strong force were slightly stronger, protons would bind into diprotons, pairs of protons without neutrons. This would radically alter nuclear chemistry. Hydrogen would quickly convert into heavier elements, leaving the universe hydrogen-free. Moreover, with a strong force, certain unstable nuclei in our universe would become stable. The periodic table would look completely different. The elements essential for chemistry, carbon, nitrogen, oxygen, might not exist or might have very different properties. The observed strength of the strong force produces a periodic table rich enough for complex chemistry, but not so chaotic that nothing is stable. This appears fine-tuned. The electron-to-proton mass ratio, the electron, is much lighter than the proton, about 1/1800th the mass. This mass ratio is crucial for chemistry. If electrons were heavier, atoms would be smaller. Chemical bonds would be different. Molecules would be more compact and less reactive. If electrons were much heavier, say, comparable to proton mass, chemistry would be radically different. Electrons might be captured by nuclei more easily, converting protons into neutrons through inverse beta decay. Atoms might be unstable. If electrons were lighter, atoms would be larger. Chemical bonds would be weaker. Molecules would be fragile. The observed mass ratio produces atoms of convenient size, small enough for quantum effects to matter, large enough for complex molecules to form. Is this fine-tuned? It depends on perspective. The ratio seems arbitrary. We don't know why the electron mass is what it is. That the value permits chemistry and chemistry permits life. The whole state and fine structure constant. Remember Fred Hoyle's prediction of a carbon resonance. The energy of this resonance depends partly on the fine structure constant, the number describing electromagnetic force strength. The fine structure constant is approximately undivided by 137. This dimensionless number appears throughout physics. It determines atomic energy levels, spectral lines, how light interacts with matter. If the fine structure constant were slightly different, the carbon resonance energy would shift. Move it a bit too high or too low, and carbon production becomes inefficient. Moreover, the fine structure constant affects the balance between carbon and oxygen production. Stars make both elements through helium fusion. The relative amounts depend on reaction rates, which depend on resonance energies, which depend on the fine structure constant. If the fine structure constant were a few percent different, stars might produce mostly oxygen with little carbon, or mostly carbon with little oxygen. Life needs both elements in substantial amounts: carbon for complex molecules, oxygen for energy metabolism, and water. The observed value produces substantial amounts of both. Another apparent coincidence: neutron lifetime and nucleosynthesis. The neutron is slightly heavier than the proton. Free neutrons decay with a half-life of about 10 minutes, converting to protons, electrons, and antineutrinos. This lifetime is crucial for Big Bang nucleosynthesis. If neutrons decayed much faster, they'd all decay to protons before having time to form helium nuclei. The universe would be pure hydrogen. If neutrons decayed much slower, or were stable, almost all hydrogen would convert to helium during Big Bang nucleosynthesis. The universe would be helium-dominated. The observed lifetime is just right to produce a universe with about 75% hydrogen and 25% helium by mass, the right proportions for stars to form and burn for billions of years. This lifetime depends on the mass difference between neutrons and protons, which depends on quark masses and the strong force. It's another example of apparent fine-tuning. The flatness of space. We mentioned earlier that the universe's spatial geometry is remarkably flat. Let's explore why this matters for life. If the universe had positive curvature shaped like a sphere, it would be finite and closed. Depending on how strongly curved, it might recollapse before stars and galaxies could form. Intelligent life would never have time to evolve. If the universe had negative curvature shaped like a satellite, it would be open and infinite. But strong negative curvature would mean matter spreads out so quickly that galaxies and stars never form. The universe would be too dilute for structure. Flatness, or very slight curvature, provides a Goldilocks zone where structure can form and last long enough for complexity to emerge. As mentioned, inflation naturally produces flatness by exponentially expanding space. But inflation itself requires fine-tuning of the inflating potential. So we've traded one fine-tuning problem for another. This is a recurring theme in cosmology: the temperature of the cosmic microwave background. The cosmic microwave background radiation light from the early universe has a temperature of about 2.7 Kelvin today. This temperature results from the universe's expansion cooling the initially hot radiation. If the universe expanded much faster, the CMB would be cooler. If it expanded slower, the CMB would be warmer. But the temperature isn't arbitrary. It affects when atoms first formed. In the early universe, matter was ionized electrons stripped from nuclei by energetic photons. As the universe cooled, electrons combined with nuclei to form neutral atoms. This happened when the universe was about 380,000 years old at a temperature of roughly 3000 Kelvin. If conditions were significantly different, recombination might have occurred earlier or later, affecting structure formation. Earlier recombination would mean matter starts clumping sooner. Later recombination delays structure formation. The observed timing produces a universe where galaxies form at intermediate times, not too early, when the universe is still very dense and chaotic, not too late when expansion has diluted everything too much. Again, the conditions seem well suited for complexity to emerge. Galaxy formation and dark matter. Dark matter plays a crucial role in structure formation. Without it, galaxies wouldn't form as we observe. In the early universe, matter was almost perfectly smooth. Tiny quantum fluctuations, 1 part in 100,000 density variations, seeded structure formation. Denser regions attracted more matter through gravity and slowly grew. But ordinary matter couldn't have done this alone. Ordinary matter interacts with radiation, which opposes gravitational collapse. Photons push on electrons, preventing matter from clumping efficiently. Dark matter doesn't interact with radiation. It can clump freely. Dark matter collapsed first, creating gravitational wells that ordinary matter eventually fell into. Without dark matter, galaxy formation would be delayed or prevented. The amount of dark matter also matters. Too much, and structures collapse too quickly, forming massive objects early on. Too little, and structures form too slowly or not at all. The observed dark matter density is, again, seemingly well suited for forming galaxies of the right size at the right times. Stellar lifetimes and element production stars need to live long enough for planets to form and life to evolve. The Sun has been shining steadily for about 4.6 billion years and will continue for another 5 billion. This timescale depends on several factors. The star's mass determines how long it lets more massive stars burn hotter and faster. The gravitational constant determines how tightly matter collapses and how much pressure exists at the core, affecting fusion rates. If gravity were stronger, stars would burn faster. They'd exhaust fuel in millions of years instead of billions. Not enough time for complex life to evolve on planets. If gravity were weaker, stars might not ignite at all, or they'd burn so slowly that they produce insufficient energy for habitable planets. The observed strength of gravity produces stars with a wide range of lifetimes. Small stars live trillions of years. Medium stars like the Sun live billions. Massive stars live millions. This diversity is important. Massive short-lived stars produce and disperse heavy elements through supernovae. Medium-lived stars provide stable environments for planets. Small, long-lived stars will dominate in the far future. Supernova nucleosynthesis. Speaking of supernovae, these stellar explosions are essential for producing many elements heavier than iron. Fusion in stellar cores produces elements up to iron, but iron is the most stable nucleus. Fusing it consumes energy rather than releasing it. So stellar fusion stops at iron. Heavier elements copper, silver, gold, uranium require energy input. They're produced during supernova explosions when enormous energy and neutron fluxes create rapid nuclear reactions. Without supernovae, the universe would have no gold, no uranium, no thorium, none of the actinides. The periodic table would end at iron. Supernovae depend on specific stellar physics. The core collapse must be violent enough to expel the outer layers, dispersing elements into space. This depends on neutrino physics, the equation of state of ultradense matter, and numerous other factors. If physics were slightly different, supernovae might not occur or might not efficiently produce heavy elements. The universe would be impoverished of the rich chemistry we observe. Planetary formation and habitable zones for life to emerge. You need not just the right universe and the right stars, but also the right planets. Rocky planets like Earth require heavy elements: silicon, iron, magnesium, oxygen. These elements must be present in sufficient quantities and form solids rather than remaining in gaseous form. This depends on temperatures and pressures in the protoplanetary disk, the cloud of gas and dust orbiting young stars where planets form. The temperatures depend on the star's luminosity and the distance from the star. There's a habitable zone around each star where temperatures permit liquid water. On a planet's surface, too close, water boils away. Too far, it freezes. For some like stars, this zone is roughly where Earth orbits, but the zone's existence and width depend on numerous factors including the star's temperature, the planet's atmosphere, greenhouse effects, and more. If fundamental constants were different, affecting stellar properties, habitable zones might not exist or might be so narrow that planets rarely fall within them. Atmospheric retention and planetary mass. A planet needs sufficient gravity to retain an atmosphere, but not so much gravity that the atmosphere is crushing or the planet is gaseous like Jupiter. Earth's mass is just right to retain water vapor, nitrogen, and oxygen while allowing hydrogen and helium to escape. This depends on the balance between thermal speeds of atmospheric molecules and the planet's escape velocity. If Earth were less massive, it couldn't hold much atmosphere. Water would escape into space. If Earth were more massive, it might retain to thicken atmosphere or accrete hydrogen, becoming a mini Neptune. This balance depends on planetary formation physics, which depends on stellar properties, which depend on fundamental constants. The chain of dependencies is long, but each link must work for habitable planets to exist. The stability of planetary orbits. Planets need stable orbits over billions of years. Earth's orbit has remained in the habitable zone throughout its history, allowing life to evolve and persist. Orbital stability depends on gravitational dynamics. In our solar system, Jupiter acts as a guardian, its massive gravity deflecting comets and asteroids that might otherwise bombard Earth more frequently. But Jupiter also destabilizes some orbits. The asteroid belt between Mars and Jupiter is prevented from forming a planet by Jupiter's gravitational perturbations. The configuration of our solar system, the masses and positions of planets, appears fortunate. Many possible configurations would be unstable or result in planets migrating dramatically over time. Simulations show that planetary systems can be chaotic. Small changes in initial conditions lead to vastly different outcomes. Some systems eject planets, others send planets crashing into stars. Our solar system's stability over billions of years seems lucky. Whether this is selection bias, we can only observe systems stable enough for life, or genuine fine-tuning, is debated. To Moon and Earth stability, Earth's moon plays an important role in maintaining Earth's climate stability. The moon stabilizes Earth's axial tilt, the angle between Earth's rotation axis and orbital plane. Without the moon, Earth's tilt would vary chaotically due to gravitational perturbations for other planets. Over millions of years, the tilt might swing from near 0 to 90 degrees or more. This would cause dramatic climate swings, ice ages, runaway greenhousings, extreme seasonal variations. The moon's gravity prevents this, keeping Earth's tilt around 23.5 degrees with only minor variations. This provides stable seasons over geological time, allowing life to adapt and thrive. The moon formed from a giant impact early in Earth's history. A Mars-sized object collided with proto-Earth, and debris coalesced into the moon. This event seems random, yet it provided crucial stability for life's evolution. Is this fine-tuning, or just good fortune? It's hard to say. Many planets don't have large moons, but maybe planets with life typically need such stabilizers, and we find ourselves on one because unstable planets don't develop observers. The Cambrian explosion and oxygenation. Earth's history shows that life's emergence and evolution depend on specific planetary conditions developing at the right times. For billions of years after life arose on Earth, it remained simple, mostly single-celled microorganisms. Complex multicellular life didn't appear until about 600 million years ago, in the Cambrian explosion. One factor enabling this was oxygen. Early Earth had little atmospheric oxygen. Photosynthetic organisms gradually released oxygen over billions of years. Only when oxygen levels rose sufficiently could large complex animals evolve. They need oxygen for efficient metabolism. This oxygenation depended on specific biology and geology. The timing had to work out. If oxygenation happened too early, before the sun brightened enough, Earth might have frozen over. Too late, and the sun's increasing brightness might make Earth too hot before complex life could emerge. Again, the timing seems fortuitous. Whether this is luck, anthropic selection, or fine-tuning of planetary properties is unclear. The question of extraterrestrial life: if the universe is fine-tuned for life, why don't we see evidence of other civilizations? This is the Fermi paradox. Given the universe's age and size, and given that life emerged on Earth relatively quickly once conditions permitted, we might expect intelligent life to be common. Some civilizations should be billions of years ahead of us technologically. Where are they? Several answers are possible. Maybe intelligent life is rare, we're early or alone. Maybe civilizations typically self-destruct. Maybe they're out there but we can't detect them yet. Maybe they're deliberately hiding or ignoring us. Or maybe the fine-tuning isn't perfect. Maybe conditions for life are rare even in a fine-tuned universe. Earth might require numerous improbable events: the moon forming impact, plate tectonics, Jupiter's protective presence, a stable star, a galactic location safe from supernovae and other hazards. If life requires this many coincidences, we might be alone or nearly alone in our galaxy. Even if life is possible, this doesn't resolve the fine-tuning question, but adds another layer to it. The simulation hypothesis. A different explanation for apparent fine-tuning is that we're living in a simulation created by advanced beings. If civilization eventually develops the technology to create detailed simulations of universes, complete with physics, chemistry, evolution, consciousness, then simulated universes might vastly outnumber real ones. If most universes are simulations, we're probably in one. And simulated universes would be designed with specific goals, possibly including the emergence of life and consciousness. The fine-tuning would be intentional design by the simulators. This is speculative and unfalsifiable. There is no way to test whether we're in a simulation. but some physicists and philosophers take it seriously. The simulation hypothesis combines elements of design and multiverse thinking. Instead of a supernatural designer, we have advanced technological civilizations. Instead of infinite physical universes, we have infinite simulated ones. Whether this is more plausible than other explanations is debatable. The doomsday argument, proposed by astrophysicist Brandon Carter, uses anthropic reasoning to estimate humanity's future lifetime. The argument goes, if humans are typical observers, we're probably somewhere around the middle of humanity's total population timeline. We're probably not extraordinarily early or extraordinarily late. Current humans number in the tens of billions, and counting all who have ever lived. If humanity lasts millions of years, trillions or quadrillions of humans will live. We'd be among the very first, which seems unlikely if we're typical. Therefore, humanity probably won't last that long. We might have only centuries or millennia remaining, not millions of years. This conclusion is disturbing and controversial. Critics argue the reasoning is flawed. There's no reason to assume we're typical in this sense. Supporters argue is valid anthropic reasoning similar to what we use for fine-tuning. The doomsday argument shows that anthropic reasoning can lead to uncomfortable conclusions, not just interesting cosmological speculations. Probability and the anthropic principle. One challenge with anthropic reasoning is understanding probability in unique events. If there's only one universe, asking what's the probability it would have these constants is unclear. Probability applies to repeated trials. You can't meaningfully talk about the probability of a unique event. But if there are many universes, whether in a multiverse or through repeated Big Bangs, then probability makes sense. We can ask, given many universes with random constants, what fraction permits life? If that fraction is tiny but the total number is vast, finding ourselves in a life-permitting universe isn't surprising. It's anthropic selection. Without a multiverse, fine-tuning seems inexplicable by chance. With a multiverse, it's expected. This is why the multiverse hypothesis is so attractive to many physicists. Despite being unfalsifiable, it makes the apparently improbable probable. The measure problem in eternal inflation. If eternal inflation produces infinitely many pocket universes, how do we calculate probabilities? In an infinite multiverse, everything that can happen does happen infinitely often. There are infinitely many universes, like ours, infinitely many slightly different, infinitely many drastically different. Given infinities, how do we say one outcome is more probable than another? This is the measure problem, defining a probability measure on an infinite set of universes. Different measures give different predictions. Some predict we should observe this, others predict that. Without knowing the right measure, eternal inflation doesn't make testable predictions. Physicists have proposed various solutions cutting off the infinities at some time, weighing universes differently, using observers rather than volumes. None is entirely satisfactory. The measure problem is one of eternal inflation's deepest challenges. Testing anthropic predictions. Can anthropic reasoning make testable predictions? Some claim yes. For example, if the cosmological constant comes from anthropic selection in a multiverse, we can predict what value observers should typically see. Calculations suggest we should observe a value near the minimum needed for galaxies to form. The actual value is within the predicted range, not at the absolute minimum, but relatively close. Some see this as confirming anthropic reasoning. Another prediction: we shouldn't observe constants that seem unnecessarily well-tuned. If anthropic selection is correct, constants should be near the boundary of life-permitting values, not deep in the safe zone. For most constants, this seems true. The carbon resonance could be a bit higher or lower. The cosmological constant could be somewhat larger. They're in the permissible range, but not far from the boundaries. If we found constants unnecessarily well-tuned, much safer than needed for life, that would challenge anthropic explanations and suggest design. The role of consciousness. Some versions of the anthropic principle emphasize consciousness specifically, not just life. The strong anthropic principle sometimes includes claims that the universe must produce conscious observers, not merely living organisms. This raises philosophical questions. What is consciousness? Does it require brains? Or could I be conscious? Could simple organisms be conscious in some sense? If consciousness requires specific types of neural complexity found only in mammals, the fine-tuning becomes even more striking. Not only must physics permit chemistry and life, it must permit evolution of large brains. Some quantum mechanics interpretations, like von Neumann's, give consciousness a fundamental role in collapsing wave functions. In this view, consciousness isn't just an accident but essential to reality itself. These ideas are highly speculative and controversial. Most physicists avoid them, that they represent one extreme interpretation of anthropic thinking. Fine-tuning and God. The fine-tuning argument is often invoked in debates about God's existence. It's framed as evidence for a creator who designed the universe for life. Theologians and philosophers like William Lane Craig argue that fine-tuning is better explained by design than by chance or multiverse. A designer who wants to create life would naturally tune constants appropriately. Critics respond that this doesn't specify which god or designer. It doesn't tell us anything about the designer's properties, and it raises the question of who designed the designer. Moreover, the multiverse hypothesis, while unproven, is scientifically motivated by inflation theory and string theory. It's not ad hoc, so invoking design may be premature. To debate parallels older design arguments like Paley's watchmaker analogy. Finding a watch implies a watchmaker. Finding a fine-tuned universe implies universe maker. But Darwinian evolution showed that apparent design in biology arises naturally without a designer. Could something similar explain cosmic fine-tuning? The Darwinian analogy, before Darwin, biological complexity seemed to require a designer. The human eye, the bird's wing, the intricate machinery of cells, how could these arise by chance? Darwin showed they arise through natural selection. Random mutations create variation. Beneficial variations spread. Over millions of generations, complexity accumulates without design. Could cosmic fine-tuning work similarly? Could universes undergo some sort of selection? Lee Smolin proposed cosmic natural selection. In this hypothesis, black holes spawn baby universes with slightly different constants. Universes that make many black holes produce many offspring. Constants are selected for black hole production. Interestingly, constants that favor black holes also tend to favor stars, which may favor life. So we might exist in a universe descended from many black hole-producing universes, with constants optimized for that purpose. This is speculative and difficult to test, but it shows that Darwinian thinking might apply to cosmology. The landscape of possibilities. String theory's landscape. The vast number of possible vacuum states provides a concrete framework for thinking about fine-tuning. If the landscape is real and all possibilities are realized somewhere in eternal inflation, then we have a well-motivated multiverse. Fine-tuning becomes selection bias. But critics argue the landscape is so vast that it predicts everything and nothing. Any observation can be explained by saying that happened somewhere in the landscape. String theorists respond that we can make statistical predictions. Most points in the landscape should have certain properties. If our universe doesn't match typical properties, that would be evidence against the landscape picture. The debate continues. String theory remains unconfirmed. The landscape is mathematically real, but physically uncertain. Conclusion. Living with mystery. After exploring fine-tuning from every angle, what can we conclude? The fine-tuning is real. The constants do appear improbably well-suited for life. This is an empirical fact, not philosophy. The explanations are uncertain. Multiverse, design, chance, unknown physics. Each has adherents and critics. None is proven. For now, we must live with mystery. We don't know why the universe permits our existence. We don't know if we're alone, typical, or special. This is both humbling and exhilarating. We're part of something we don't fully understand. The deepest questions about existence remain open. Science will continue investigating. Better observations will constrain theories. New physics might emerge that changes everything. Or we might never know. Some questions may be unanswerable, lost beyond the limits of what we can observe or test. But the quest itself is meaningful. Trying to understand, even knowing we might fail, defines us as a species. We're conscious matter pondering its own existence in a cosmos that seems calibrated for us. Whether by design, chance, or selection, we're here. And while we're here, we can wonder, explore, and search for answers. That might be the only certainty in this cosmic puzzle. That seeking understanding is itself part of what makes us human. And perhaps that's enough. The future of fine-tuning research. What comes next in our quest to understand cosmic fine-tuning? Several promising directions exist. First, improved cosmological observations will better constrain fundamental constants. The James Webb Space Telescope and future instruments will observe distant galaxies with unprecedented precision. By studying how the universe evolved at different cosmic epochs, we can test whether constants truly are constant or whether they change over time. Some theories predict constants might vary slightly across space or time. Finding such variations would revolutionize physics and might explain apparent fine-tuning. We exist in a region or era with life-permitting values. Second, particle physics experiments continue probing the Standard Model's limits. The Large Hadron Collider and planned future colliders might discover new particles or forces. These discoveries could reveal why constants have their observed values. For instance, finding supersymmetric particles would solve the hierarchy problem and explain why the Higgs mass is so light. This would remove one apparent fine-tuning. Third, quantum gravity research might illuminate why physical laws have their form. String theory, loop quantum gravity, and other approaches might predict specific values for constants, rather than treating them as free parameters. If a fundamental theory uniquely determines all constants, fine-tuning becomes explain the constants must be what they are, because deeper mathematics requires it. Fourth, cosmologists are searching for evidence of other universes. While directly observing other universes seems impossible, subtle signatures might exist. Collisions between bubble universes in eternal inflation might leave marks in the cosmic microwave background, circular patterns, or temperature anomalies. None have been conclusively detected, but searches continue. Finding evidence for other universes would strongly support the multiverse explanation for fine-tuning. The anthropic shadow effect here is a subtle but important consequence of anthropic reasoning, called the anthropic shadow. If dangerous phenomena are likely to destroy observers, we'll systematically underestimate those phenomana's frequency. We can only exist to make observations in cases where the dangerous events didn't occur. For example, suppose gamma ray bursts enormously energetic explosions from collapsing star-sterilized planets. In their galaxies, if bursts are common, few planets develop intelligent life. The intelligent life that does emerge exists in rare galaxies with few bursts. Those observers would look around and see few bursts, concluding bursts are rare. That they be wrong, bursts are common, but observers can only exist where they're rare. This is the anthropic shadow. The effect applies to any existential risk, asteroid impacts, supervolcano eruptions, vacuum decay. If these are common and fatal, we'll underestimate their frequency because we can only observe from timelines where they haven't occurred. This has implications for risk assessment. Events that could destroy civilization might be more likely than our historical record suggests. Vacuum stability and the Higgs field. Speaking of vacuum decay, there's a troubling possibility involving the Higgs field. The Higgs might not be in a truly stable configuration. It might be in a metastable state, stable for now, but not the absolute lowest energy state. If a quantum fluctuation somewhere in space nudges the Higgs field into its true lowest energy state, a bubble of true vacuum would form and expand at light speed, destroying everything in its path. The Higgs field inside the bubble would have different properties, changing particle masses and possibly making atoms impossible. Calculations suggest our vacuum might be metastable. It could last trillions of years, or it could decay tomorrow. We can't predict when. Is this fine-tuning? Some argue yes. In most universes, the Higgs might be truly unstable, decaying instantly, or it might decay so frequently that life never has time to emerge. We exist in a universe where decay is rare enough for billions of years to pass safely. Alternatively, maybe our calculations are wrong and the vacuum is truly stable. More precise measurements of particle masses will help determine which. The dimensionality of spacetime revisited. We mentioned that 3 spatial dimensions seem necessary for life. Let's explore this more deeply. In 2 dimensions, gravity works differently. The force between masses doesn't fall off with distance the way it does in 3 dimensions. Orbits would be unstable. Atomic structure would be completely different. Complex chemistry might be impossible. In 4 or more spatial dimensions, electromagnetism and gravity have different mathematical forms. The inverse square law becomes inverse cube, or stronger. This makes planetary orbits so unstable planets spiral into stars, or escape to infinity over short timescales. Atomic orbitals also become unstable in 4 dimensions. Electrons can't maintain stable orbits around nuclei. Atoms as we know them wouldn't exist. Moreover, certain mathematical theorems about differential equations change with dimensionality. The equations governing electromagnetic radiation have special properties in 3 spatial dimensions that break down in other dimensionalities. String theory proposes extra dimensions beyond the 3 we observe. That these are supposedly compactified, curled up at tiny scales. Only 3 dimensions are large. Why 3? Is this determined by deeper mathematics, or is it anthropic selection? In a multiverse with different dimensionalities, only universes with 3 large spatial dimensions could support observers. Time's arrow and the past hypothesis, the second law of thermodynamics, entropy increases over time, gives time a direction. We remember the past, not the future. Eggs break but don't unbreak. This arrow of time depends on the universe starting in a low entropy state. If the Big Bang began with maximum entropy, time would have no direction. There would be no distinction between past and future. The universe's initial low entropy is itself a form of fine-tuning. Roger Penrose calculated that the probability of such a low entropy beginning is absurdly small, 1 part in 10 to the power of 10 to the power of 123. This is called the past hypothesis, the assumption that the universe began in a special low entropy state. Without it, statistical mechanics doesn't work properly. We can't explain why entropy increases. Some physicists propose that the low entropy beginning is explained by inflation. Inflation stretches space so smooth that entropy is automatically low. But then we need to explain why inflation occurred, which requires its own fine-tuning. Alternatively, maybe the low entropy is anthropic. Only universes with low entropy beginnings have arrows of time, and thus evolution, memory, consciousness. We couldn't exist in high-entropy universes, so we don't observe them. The Boltzmann brain problem. Here's a disturbing thought experiment. In an infinite universe with infinite time, thermal fluctuations will eventually produce anything, no matter how improbable. This includes fully formed brains with false memories of lives that never occurred. These Boltzmann brains pop into existence randomly, exist briefly, then dissipate. In certain cosmological models, especially those with eternally accelerating expansion, Boltzmann brains vastly outnumber normal observers like us. If so, we should expect to be Boltzmann brains with false memories rather than real people. But we seem to be real people. This suggests something is wrong with models that predict too many Boltzmann brains. It's an anthropic constraint on cosmology. The Boltzmann brain problem shows that anthropic reasoning can lead to weird places. It's one reason some physicists are uncomfortable with multiverse theories. The quantum vacuum and zero-point energy, even empty space, has energy due to quantum fluctuations. This zero-point energy contributes to the cosmological constant. Naively calculating this contribution gives an absurdly large number, about 10 to the power of 120 times larger than observed. This is the worst prediction in physics. Why is the vacuum energy so small? We don't know. Some mechanism must cancel almost all of it, leaving only a tiny remainder. This cancellation requires fine-tuning to incredible precision, 1 part in 10 to the 120th. That's like adjusting a knob with 10 to the 120th possible settings and hitting exactly the right one. Some physicists hope supersymmetry provides the cancellation mechanism. Others invoke anthropic reasoning. In a multiverse, we exist in a rare region with small vacuum energy, because large vacuum energy prevents galaxies from forming. But neither explanation is proven. The cosmological constant problem remains one of physics' deepest mysteries. Black holes and information paradoxes. Black hole physics touches on fine-tuning in subtle ways. Stephen Hawking showed that black holes radiate and eventually evaporate, but the radiation appears thermal random, carrying no information about what fell in. This violates quantum mechanics, which says information is never destroyed. The black hole information paradox has troubled physicists for decades. Recent work suggests information is preserved through quantum entanglement between the black hole interior and exterior. As the hole evaporates, information slowly leaks out in subtle correlations. Why does this relate to fine-tuning? Because the resolution involves quantum gravity, the unknown theory unifying quantum mechanics and general relativity. Understanding quantum gravity might explain why fundamental constants have their values. Moreover, some speculate that universes might be born from black holes. If each black hole creates a new universe with slightly different constants, Lee Smolin's cosmic natural selection, then fine-tuning arises naturally through a selection process favoring black hole-producing universes. The unreasonable effectiveness of mathematics. Physicist Eugene Wigner famously pondered the unreasonable effectiveness of mathematics in describing nature. Why should abstract mathematics invented by humans correspond so precisely to physical reality? Fine-tuning is part of this puzzle. Not only does mathematics describe physics, but the specific mathematical structures we observe, the dimensionalities, symmetries, constants, seem special. Some argue this points to a mathematical universe hypothesis. Perhaps reality is fundamentally mathematical. Physical existence is just mathematics instantiated somehow. The constants aren't arbitrary, but mathematically necessary. Others argue that we invent mathematics to describe what we observe, so of course it's effective. We create mathematical tools that work for our universe. In a different universe, beings would develop different mathematics. This philosophical rabbit hole goes deep. Is mathematics discovered or invented? Are mathematical truths objective or contingent? Does mathematics exist independently of physical reality? These questions connect to fine-tuning because they ask whether the universe's properties are necessary or contingent, mathematical or physical, unique or one among many possibilities. Quantum mechanics and observer selection, some interpretations of quantum mechanics, tie directly to anthropic reasoning. In Navarrete's many worlds interpretation, every quantum measurement spawns new branches of reality. All outcomes occur, just in different branches. If this is true, then there are countless copies of you in different branches experiencing different measurement results. Most of those branches might be uninhabitable. Perhaps quantum fluctuations in the early universe led to no galaxy formation, but in rare branches, fluctuations seeded structures perfectly, leading to galaxies, stars, planets, and life. You necessarily find yourself in such a branch because you couldn't exist in the others. This is anthropic selection taken to an extreme. Not just selection among different universes, but among different branches of quantum reality. Whether many worlds is correct remains debated, but if true, it provides a natural framework for anthropic reasoning without requiring a multiverse of separate universes. The cosmic microwave background, anomalies. The cosmic microwave background, the afterglow of the Big Bang, is remarkably uniform, but contains tiny temperature variations. These variations match inflation's predictions beautifully. However, some anomalies exist. Large-scale patterns seem slightly odd. The cold spot is colder and larger than expected. The axis of evil suggests a preferred direction in space, contradicting the assumption that the universe is isotropic. These might be statistical flukes. Look at enough data and you'll find anomalies. Or they might be evidence of something deeper. Some speculate these anomalies could be signatures of other universes colliding with ours in eternal inflation. Others propose they reflect exotic physics in the very early universe. If real, these anomalies might eventually help test the multiverse hypothesis. Collisions between bubble universes would leave specific patterns that differ from random fluctuations. Ongoing and future observations will determine whether the anomalies are significant or just noise. Neutrino masses and the seesaw mechanism. Neutrinos, the ghostly particles that barely interact with matter, have tiny but non-zero masses. Why are neutrino masses so much smaller than other particle masses? One explanation is the seesaw mechanism. If extremely heavy right-handed neutrinos exist near the grand unification scale, around 10 to the 16th billion electron volts, they could give ordinary neutrinos tiny masses. Through quantum mechanical mixing, the seesaw mechanism is elegant but introduces new fine-tuning. Why do right-handed neutrinos have such large masses? And why do the mixing parameters conspire to give exactly the small masses we observe? Neutrino masses affect cosmology. If they were much larger, neutrinos would be hot dark matter, smearing out cosmic structure. If they were zero, certain subtle astronomical observations would be different. The observed values permit the structure we see. Another apparent coincidence: grand unification and the desert. The Standard Model successfully describes particle physics up to energies around 100 billion electron volts, the scale explored by the Large Hadron Collider. But the fundamental forces don't appear unified at these energies. Many physicists believe that at much higher energies, the grand unification scale around 10 to the 16 billion electron volts, the electromagnetic, weak, and strong forces merge into one unified force. Between the LHC scale and the grand unification scale is a vast desert 20 orders of magnitude, with supposedly no new physics. Why is there such a desert? Why is grand unification so far beyond our reach? This hierarchy between scales seems fine-tuned. If new physics appeared at intermediate scales, it would likely destabilize the Higgs mass. The desert might be necessary for the Standard Model to work. Or perhaps the desert isn't real. Perhaps new physics exists at intermediate scales, but is subtle or difficult to detect. Future discoveries might fill in the desert. Proton decay and stability. In grand unified theories, protons can decay into lighter particles. The proton lifetime is predicted to be around 10 to the 35th years, far longer than the universe's age. Experiments have searched for proton decay for decades without finding it. This sets lower limits on the proton lifetime, at least 10 to the 34th years, possibly much longer. Why are protons so stable? In most grand unified theories, various parameters must be fine-tuned to make the proton lifetime long enough. Otherwise, protons would decay quickly, and matter wouldn't exist. The stability of matter depends on these fine-tunings. Change the parameters slightly, and protons decay in microseconds. No atoms, no chemistry, no life. The strong CP problem, quantum chromodynamics. The theory of the strong nuclear force has a parameter called theta that describes how much the strong force violates charge parity symmetry. Experimentally, theta is extraordinarily small, less than 10 to the minus 10th, but there's no reason in the theory why it should be small. It could be any value from 0 to 2 pi. Why is theta so small? This is the strong CP problem. A small theta is needed to avoid certain experimental consequences, like the neutron having an electric dipole moment much larger than observed. One solution is the axion, a hypothetical particle we mentioned earlier as a dark matter candidate. The axion dynamically drives theta to 0, solving the CP problem. But if axions don't exist, the small theta value is unexplained fine-tuning. Nature chose a very specific value out of a large range of possibilities, and that value happens to be necessary for the universe to work properly. The muon G2 anomaly. The muon is a heavier cousin of the electron. Its magnetic moment, how strongly responds to magnetic fields, has been measured with extraordinary precision. Recent experiments show the measured value differs slightly from standard model predictions. The discrepancy is small but statistically significant. If confirmed, this suggests new physics beyond the standard model. Perhaps new particles or forces exist that affect the muon but haven't been directly detected yet. Why mention this in a discussion of fine-tuning? Because any new physics must be carefully balanced. The new contributions must be just right to avoid causing other problems. If the new physics is too strong, it would have been detected in other experiments. If it's too weak, it wouldn't explain the muon anomaly. The strength must be in a narrow range. This might be another coincidence, or it might reflect deeper structure we don't yet understand. The limits of science and the boundaries of knowledge. Let's step back and consider epistemological questions. What can science tell us about fine-tuning? What are the limits of scientific inquiry? Science works by making testable predictions and comparing them to observations. But if fine-tuning is explained by a multiverse, and we can never observe other universes, is the explanation scientific? Some argue that untestable hypotheses aren't science. The multiverse, if forever beyond observation, is metaphysics, not physics. Others respond that science often deals with unobservables. We can't see atoms or quarks directly, yet we're confident they exist because theories postulating them make successful predictions. Similarly, inflation and string theory predict a multiverse. If these theories are confirmed through other tests, say, detecting gravitational waves from inflation or finding supersymmetric particles, then the multiverse comes along as a consequence. The debate touches on what makes a theory scientific. Is testability essential, or can indirect evidence and theoretical consistency suffice? The Anthropic principle in popular culture, fine-tuning, and the Anthropic principle have captured public imagination. They appear in science fiction, philosophy, and theology. Science fiction often explores multiverses and parallel worlds. Stories like the Long Earth series or His Dark Materials imagine traveling between universes with different properties. Philosophically, fine-tuning relates to existentialism and questions of meaning. If the universe is random and meaningless, the fact that we exist at all becomes profound. If it's design, that raises questions about purpose and destiny. Theologically, fine-tuning is invoked in arguments for God's existence. Some see it as evidence of a creator. Others see multiverse explanations as threats to religious belief. These cultural dimensions show that fine-tuning resonates beyond physics. It touches fundamental human concerns about why we're here and whether existence has purpose. The psychology of fine-tuning. Human psychology affects how we perceive fine-tuning. We're pattern-seeking creatures prone to seeing design where none exists. Pareidolia, seeing faces in clouds or toast, shows how eagerly our brains find patterns. Might we be doing something similar with cosmic fine-tuning? Moreover, we're subject to confirmation bias. Once convinced the universe is fine-tuned, we notice confirming examples and ignore contrary evidence. Probability is also psychologically tricky. Rare events happen all the time. Someone wins the lottery despite astronomical odds. Existence might be like winning a cosmic lottery. Rare, but someone had to win. These psychological factors don't invalidate fine-tuning arguments, but they remind us to be careful. We should scrutinize our reasoning and check whether we're seeing patterns that truly exist, or that we're imposing. The ethics of anthropic reasoning. If we take anthropic reasoning seriously, it has ethical implications. If civilization's continuation increases the number of future observers, and anthropic selection favors populous civilizations, then we have moral reasons to ensure our survival and flourishing. Conversely, actions that risk extinction, nuclear war, ecological collapse, uncontrolled, become morally worse from an anthropic perspective. The doomsday argument raises uncomfortable questions. If we're probably near humanity's end, should we change our behavior? What obligations do we have to potential future generations? These aren't just abstract philosophy, they affect how we think about existential risks, space colonization, and our responsibility to the future. Conclusion: the persistent mystery. We've explored fine-tuning from every conceivable angle: physics, philosophy, probability, psychology, ethics. What have we learned? First, the fine-tuning is empirically real. The constants do appear special. This isn't imagination or bias, it's measurement. Second, explanations remain uncertain. Multiverse, design, deeper physics, or chance each has merits and problems. None is proven. Third, the question matters. It touches on existence's deepest mysteries. Why is there something rather than nothing? Why this universe rather than another? Why can we ask these questions? Fourth, the answer might be forever beyond reach. If the multiverse exists, but is unobservable, we might never know for sure. We'll have to accept uncertainty. But uncertainty doesn't mean giving up. Science progresses by narrowing possibilities, constraining theories, gathering evidence. Even if we can't prove the final answer, we can rule out wrong answers and approach truth asymptotically. The fine-tuning puzzle teaches humility. The universe is more mysterious than we imagined. Reality's foundations remain hidden. We're scratching the surface of something profound. Yet we're the part of the universe that can scratch that surface, where matter becomes conscious, pondering its own existence. Whatever the explanation for fine-tuning, the fact remains inspiring. Whether we're alone in a designed universe, typical inhabitants of an infinite multiverse, or something we haven't conceived, we're here. We can wonder, we can explore, we can push against the boundaries of knowledge. That might be the deepest response to fine-tuning. Not solving the puzzle, but embracing it. Living with the mystery while striving to reduce it. Accepting that existence is stranger, more contingent, more miraculous than we can fully comprehend. The universe seems made for us. Whether it actually is, or whether we're fortunate accidents in an uncaring cosmos, remains unknown. But either way, we're part of something extraordinary, and that's worth celebrating. That's worth protecting. That's worth the effort of understanding. Even if complete understanding remains forever beyond reach, the anthropic principle reminds us that we're observers in a cosmos that permits observation. That's not nothing. It's everything.